Today we are going to understand how to select a material for a design of machine element, and how do we specify some of the commonly used engineering materials, not all. Okay, to begin with, selection of materials. So here we basically look at the most general factors that one must consider while selecting it for a machine element. First one is availability. When we want to go for a design of any part or a system, the material must be available, particularly in the market, in abundant, right? If it is not available, we cannot think of a design at all. See, for example, some of the commonly available abundant materials are cast iron, aluminum, right? And scantily available materials are lead and copper, zinc, magnesium, so on. There are many. Okay, so that is why you see many of the components are made of cast iron and aluminum and alloys of iron. Then cost. So every design has a constraint, that is the cost, and we cannot cross it. So when we say cost, it includes both the cost of the material and as well as cost of processing the material into final product. So just because it is available in abundance, it doesn't mean that we have to go for it, right? Just because it is available cheaply, we must not also prefer it. So somewhere we may have to make a trade-off between cost and performance of the system, because when you select a cheap material for your part, it may not, its life will be very short. So you have to make a trade-off there. So when you have a cost as a constraint, you must not be taken you must not be taken it granted that we must select only cheap materials. You must also consider the functionality and the life of the component. Mechanical properties, yes, based on the service conditions and functional requirement, we select material properties that are suitable for the machine element. What do you mean by this service condition? Say, for example, the component, it is basically the ambience in which your part is operating, and where it will be subjected to several types of loads. For example, it could be a temperature load, it could be a wind load, and it could be a mechanical load, any other mechanical load. It could be any electrical load also, and so on, and functionality. So to achieve certain functionality, it must have enough strength and other properties like wear resistance, hardness, that we have seen already. Okay, so based on this, we select mechanical properties of material. To give some examples, let us assume the connecting rod of an international combustion engine. So when the combustion of fuel takes place within the cylinder, the connecting rod will move back and forth within the cylinder. As a consequence, it will be subjected to fluctuating loads. So this is what we call as fatigue. So here the selection criteria, the property that we use is endurance limit. We look at the endurance limit of the material, compare it and select the better one. So this we will discuss elaborately in unit 2. Similarly, the piston will have rings, right, which will move on the inner surface of the cylinder. As a consequence, it must not wear, right? Otherwise, what will happen if it wears? The combustion products, will escape out of the cylinder. Then your connecting rod may not move back and forth. So, what is a property that governs the selection here? That is hardness. Similarly, bearing materials, right, which must allow the smooth relative movement. So hence there must selection criterion is low coefficient of friction. Whereas in case of clutch and brake lining, right, the moment you press the brake pedal, what do you anticipate? The vehicle must stop, right? The rotation of the drum or the disc will help you in stopping the vehicle. So you must have very high coefficient of friction. So here coefficient of friction plays a role. So based on the application, you are selecting high coefficient of friction or low coefficient of friction. And if you're selecting material to manufacture automobile bodies and hoods, I have to shape it, I have to form it into the complex shapes, right? So when I want to do so, usually the automobile hoods are shaped by forming, metal forming methods, which means they are extensively deformed in the plastic range without any fracture. So here, plasticity of the material, the strength coefficient and strain hardening exponent govern the material selection. The third factor. Fourth, manufacturing considerations, right? So just because it is available easily and it is cheap and mechanical properties are better, it doesn't mean that you should go for it. Can I manufacture it using that particular material? See, how do you manufacture? You have basically primary processes like casting and so on, and molding, and secondary manufacturing processes where you do machining, right? And other farming operations, and tertiary manufacturing operations like finishing, right? And so on. So can I machine it easily? Can I cast it easily? That is what you must also look into. See, that is sometimes expensive material could be more economical than the low priced one, because the low priced one could be difficult to machine. Free cutting steels. This is one example of a material where it has excellent machinability. That is why they are used in high strength bolts, axles, and shafts. And wherever you want to have a complex shape, so you have to look at the castability, where when the molten metal can flow into the intricate passages of the mold, right? And when you have fabricated assemblies, so obviously the weldability becomes an important factor. And the various other manufacturing processes that we consider while selecting the material is like casting, forming operations, and welding, machining, and so on. Okay, so one must make a trade-off between availability, cost, mechanical properties, and manufacturing considerations, and optimization exercise. So you must not be carried away by only one parameter. In that case, it is very, very difficult to arrive at your required design. So this is about the most general factors that we consider while selecting a material. Now let us look at some of the iron alloys that we use in design, and the way in which it is specified as per the BIS standard. Okay, because that we will use in our problems. Cast iron, so you would have heard it and read it many times in the last 2 years. So it is basically an alloy of iron and carbon. I hope you remember that iron carbon diagram, right? So when do you call it as a cast iron? When the carbon percent is more than 2%. Okay. So does it contain only iron and carbon? No, you will also have other elements like silicon, manganese, sulfur, phosphorus, or any other elements also in the periodic table, which will be uh, very, very less. Which will be very, very less. These could be, stuck to the ore, and while processing, they may be carried away with the iron. So we have something called a steel, right? What is the difference between the steel and cast iron? Steels basically contain carbon less than 1%, and cast iron contains more than 2 to 4%. So this quantity, brings an enormous difference in the mechanical properties of steels and cast iron. So when you add carbon up to 1%, look at the properties of the steel. They have very high ductility, right? And they are very hard. And you add more than 2 to 4% cast iron, it has very high compressive strength. It can withstand very high temperature, right? So on. Many properties are there. You would have studied this in material science and metallurgy. So we basically use steels and cast iron. So let us look at some of the advantages and the disadvantages of cast iron from the design point of view. Okay, the first thing, yes, it is available abundantly. As a consequence, you can produce products on a mass scale. The tooling required for casting is very simple and inexpensive. Right? You can make you simple foundry tools can be used. You can make your pattern using a sand mold, right? So the cost of the cast iron products are very less. You don't need any dies, which are very costly, and you can give any complex shapes because their castability is very good. Okay, so without involving, and it has very high compressive strength. If you compare with steel, it is more than 3 to 5 times greater. Okay, so this is very much required in certain applications, and it also has excellent ability to damp the vibrations, and hence we use it in machine tool guides. I've used in very large lathes, milling machines and shaping machines. The guides, they are basically made up of cast iron parts because they can damp the machine tool vibrations. So when you can have such a property in your guide, your machining will be very accurate and precise, and it has more resistance to wear. And yes, it can withstand very high temperature. It says like up to 350 degrees centigrade. The properties of cast iron almost remain the same. It won't get altered, but they have low notch sensitivity. What is that notch sensitivity? Again, we will discuss in fatigue chapter. So this I will leave it here. What are the drawbacks? It has poor tensile strength, that is very less ductile, which means brittle compared to steel, and it is section sensitive. What does that mean? See, for the same chemical composition, as the thickness increase, what happens? Its tensile strength decreases, because when you manufacture a cast iron pot with thick section and thin section, right? As soon as you pour into the mold, let us assume for a thick section. So the cooling rate, thick section will take more time to cool. That is, the cooling rate is very low, right? Whereas for thin sections, the cooling rate is very high. It can cool very fast, and hence its hardness and strength will increase. You remember your cooling rate diagrams from your material science, right? And they do not undergo any significant plastic deformation before any failure. So that is why it is very dangerous to use them in applications where you require a warning before failure, and they fail catastrophically because of their brittle nature. Okay, so these are some of the drawbacks of cast iron. Yes, it has poor impact resistance because it is brittle in nature, and machinability, more important thing. Machinability of cast iron parts are very poor, though they have excellent castability. Okay, plain carbon steels. So even this we use. So there are three groups. You would have studied this in material science. I don't think so you remember it. Low carbon steel, plain carbon steel, medium carbon steel, and high carbon steel, based on the carbon percent. We usually call low carbon steel as mild steel with carbon percent less than 0.3%, and machinery steel or medium carbon steel, carbon percent ranging from 0.3 to 0.5%, and high carbon steel more than 0.5%. Free cutting steels and alloy steels. Let us look at what is free cutting steel. Free cutting steel means they can easily be machined. They are also carbon steels, but they will have along with carbon, manganese, and small percentage of sulfur or any other alloying element which will improve its machinability. Okay, usually sulfur is added, and there are other alloying elements also which will enhance machinability. Alloy steels, see, in addition to carbon, we will have more than one alloying elements to get certain beneficial effects. Usually we add these elements: silicon, manganese, nickel, chromium, molybdenum and tungsten. See, suppose if you want your alloy steel to withstand very high temperature, we will add silicon, nickel and manganese. If you want your alloy steel to be corrosion resistant, we add chromium and nickel. If you want your alloy steel to be very hard, we add molybdenum, tungsten and silicon. Okay, so depending on the requirement of the material property, we add different alloying elements in different percentages. Yes, now let us see how the steels are designated in the Bureau of Indian Standards. So steels are designated by a group of letters or numbers. They basically indicate these three aspects. One is the tensile strength, carbon content and the composition of alloying elements. How much percentage? So on the basis of tensile strength and chemical composition, they are specified two ways. A symbol Fe, Fe means iron, followed by minimum tensile strength in MPa or Newton per millimeter square, and a symbol F, lowercase e and uppercase e, followed by yield strength in MPa. So in your data book, you can see this. Fe360 means iron with a ultimate tensile strength or just tensile strength of 360 MPa. Similarly, FEE250 means when you see capital E, it means that the number which follows it is an yield strength. This is one way of specifying steel based on the tensile and the yield strength. So please browse through your data book to familiarize yourself, because we will be using these symbols while solving the problem. In the problem would simply specify Fe360. You may have to take this number and employ in your problem. Okay, we may not directly give all the problem. How these plain carbon steels are specified. So please remember plain carbon steel. What does it mean? We have low carbon, high carbon, medium carbon. Okay. So you will have a figure indicating 100 times the average percentage of carbon, a letter C, and then a figure indicating 10 times the average. See, please note that this is the average percentage. Okay, average percentage, because you cannot manufacture an alloy exactly to a given quantity of chemical composition. It is not possible. So we always use average percentage. Even you take any research articles, right? So they would be trying to understand the mechanical behavior of different alloys that are manufactured in their own laboratory. They might target to some percent, right? But they could be able to achieve only very less, because some would go through the slag, some would escape in the air, right? So there will be losses in different forms. So that is why they add more than what is required while casting, and then when they check the chemical composition, it will vary from point to point, and then they will take the average one. So here 55C4, first example, is a plain carbon steel. What does 55 mean? A figure indicating 100 times the average percentage. 55 is already multiplied with 100 already. So what is the percentage of carbon now? 0.55. Right, and then C, a letter C, that means it is carbon. And 4, what does 4 indicate? It is 10 times the average percentage. 4 is already, this number is already multiplied with 4, which means you have to divide it by 10. So 0.4% of manganese. So for plain carbon steels, the first number has to be divided by 100 and the last number has to be divided by 10. The first number indicates the average percentage of carbon, while the last number indicates the average percentage of manganese. So we will not add any symbol over here. Now let us go the reverse way. You are given with composition, then how do you designate it as per BIS standard? So a steel with 0.35 to 0.45% carbon. You take the average is 0.4% of carbon now, and 0.7 to 0.9% of manganese. Take the average, that is 0.8. So how do you know the carbon content now? 0.4% multiplied by 100, 40, a letter C, and then 10 times 0.8 into 10, that is 8, 40 C8. We have got it. Very simple. So these kind of chemicals, way of representation can be seen in data books also. So you must familiarize you. Molybdenum, the multiplication factor is 10. So the term high alloy steel is used for steels containing more than 10%, and the designation is, this is the way we will have a letter X. First letter is X, and then you will have a figure indicating 100 times the average percentage of carbon, and then chemical symbol of all the alloying elements, followed by a figure for its average percentage. They will be rounded off to nearest integer sometimes, and then again a chemical symbol to indicate any specially added element to. So here X 15 Cr 25 Ni 12, what does it mean? X, the moment you see X, it means high alloy steel. That means alloying element more than 10%. 15 divided by 100, 0.15% carbon, chromium 25% chromium, 12% nickel. So here the percentage will be given directly. So you don't need to multiply it by a multiplication factor or divide it by any other number, okay, in case of high alloy steel. Second example, compositions are given. How do you represent it? Take the average percentage. Average content of carbon is 0.2. Similarly, what about silicon and then manganese? They are less than 1%, so you can ignore them safely, right? So you can consider nickel and chromium. So the designation will be X20 Cr18 Ni2. Okay, 0.2% carbon. So multiplied by 100, you will get 20. And nickel is 2% and chromium is 18%. So this is about the representation of the commonly used steels and alloys. Okay, these are the references I've used. There you can borrow it from these references. Thank you.